Okay, so we can start. So the plan for today is that we have to do the final evaluation on the questionnaire. Well, on Brightspace, there's a questionnaire. And as tradition, I brought cake for the break after you've done the evaluation. Uh, so then after we're done with the evaluation, we'll do an overview on categorization models. It's not one I'm super satisfied on how to systematize all possible models of categorization, but it's what's out there in the literature, and then we can be critical about that. And then we will zoom in a specific example of a categorization model, which is the contextual generalized contextual model, because it's been a workhorse in the field, and we will see how to code it in the usual way. And then I've prepared course notes on different kinds of models that we don't get to cover with the same details. So we might do a bit of inverted classroom next time, where I will ask you to check the course notes in advance. So for the final evaluation, you should all have access to that on Brightspace. And we'll take, I don't know, 10, 15 minutes so that we're sure that it gets filled in. And then next time or the final lecture, I will present an overview of that to discuss. So if you don't have access to it on Brightspace, just let me know and I'll put a QR code on the screen. Okay, so what we've been doing last week was to discuss models of categorization. That is, ways that we could formalize the processes underlying the way you were playing the alien game. And this is something that's been very present in the debate on formalized models of cognition, because it lies at the bottom of how we acquire knowledge structure that enable an agent to make predictive inference. So by having a system to categorize the word into boxes, we have a simplified way of acting into the word. And so uh, one of the reasons that we use that danger versus nutrition dichotomy in the alien game was that a lot of the literature talks about learning how to act in the world at a very basic level, that is what you should go towards versus move away from, and what you can put in your mouth versus not put in your mouth, right? Which is something that can be created as a model also in a lot of animal models. So the question is, how do we categorize? And I think I've already covered this last week, but very quickly, right? There's a classical approach, which is about creating a logical structure that determines the category of an item, given some sufficient or necessary features, right? So things are dangerous as soon as they start growling, right? And that's a necessary condition, or sorry, sufficient condition for something to be dangerous, and the kid will move away. These kind of categorization processes didn't seem to describe a lot of the pieces of the word that we need to categorize. And an example that is used very often is the idea of birds, right? What is a necessary or sufficient condition for a bird when in the same category you have ostriches and rabbits? Which led to this idea of the prototype revolution, which was also something that resonated a lot with what was happening in computer science, with the establishment of fuzzy logic, that is logics that had intermediate values between 0 and 1. And the idea that instead of trying to find the logical rule, you would just place a bunch of your birds that you meet in a feature space. And then the idea is that the category is this fuzzy uh, set of animals, and that there might be some features which are a bit more centrals, like wings, but and flying, but you have space for stuff like ostriches who don't fly and penguins who swim, right? And this kind of approach was very elegant, but it was deemed like maybe beyond what we could imagine a categorization process could do. Why can't we actually go much simpler and say that individuals will just store the actual exemplars there, and then as they meet a new bird, right, then they're gonna look at how it resembles all these exemplars, and then we'll look at, I don't know, all the exemplars of cats, and then we'll see how it resembles all of these exemplars, and then we can sort of make an informed decision as to where it should fit in. And this would have a good um, case study exactly in these ideas of if we have things like ostriches, then like an emu is going to be easier to categorize if we actually remember the ostriches and not just this fluffy thing at the center. And this has been the dominant approach. It's actually something that underlies quite strongly current neural network approaches. That's how they seem to work. There's lots of different implementations of that, but it also sort of fell flat when it tries to describe the way that we do categorization as social linguistic animals. So as we discuss, what is a good stand model? What is a categorization model if we want to go very meta, right? We put things into words. We try to define to find definitions, and these definitions, however minimal, they become part of our categorization process, which sort of brought back the idea of some sort of logical form of these categories, but in a more Bayesian framework. So instead of having necessary and sufficient conditions, we might actually have a bunch of formal definitions of what a bird is, of what a dangerous alien is, and we might attribute a certain probability to each of these rules to be true. Right? And as we meet exemplars in the word, what we can do is we can adjust, update the probability of each of these rules being true, but also sample new rules and develop new things. Yes. Mm-hmm. Mm-hmm. Yep. Mm-hmm. Mm-hmm. Uh, so there is a lot of research on the Chinese buffet, I think it's called, problem. That is, you have cases in which you don't know how many categories there are out there and which categories are out there. And so the idea is that as you meet these exemplars, you can sort of try to figure out how to apply different categorical structures to them. To be honest, I'm not very familiar on that specific literature. Um, the problem gets very complicated very quickly. Yeah. But I suspect that there's, you know, as usual, these are all models of very specific aspects of how we categorize. And I imagine that any real world system will combine different aspects of these models. Yeah. Good. So if we try to attempt at systematizing how these different models can be structured so that we have a template that we can use also as a guide for your own models, there is a first step, which is how do we represent the inputs, right? And in the alien case, right, we were kind of lucky because what we have is we have 5 features. Well, you are kind of lucky we designed it that way. And they're represented as a sequence of possible 0 and 1s, right? However, right, we might imagine building a categorization system that instead takes actually the pixels of the aliens and fits it through a neural network of sort. The second aspect that we have is that whatever the representation is, whether it's a bunch of pixels, which are then expanded and turned down and then expanded again, etc., in a convolutional neural network, or whether we have a string of 5 binary values, we also need to identify what is relevant for the problem at hand, right? So it is a good idea to have a representation system which is more agnostic and an attentional system that in context tells us what's relevant for the problem at hand. And you've experienced that firsthand last week as the rules would change while you were playing. So if legs were not relevant at a certain point, they might actually become relevant at a different point. Then you have intermediate representation, which is how do you combine your attentional processes with the representation with the feature, sorry, in order to get something on which you actually make your inference. And we'll see examples. Then there's how do we calculate, given this representation, whether the exemplar belong to category 1 or 2 or 3 or so on and so forth. And finally, given that we decided that one category is more probable than the other, how do we actually make a final decision? Right? And if you remember, just as a spoiler, right, As we've seen in previous models, you can then make sigmoid, which has more or less temperature in order to make the system more or less deterministic. Right? And then there's something that is often forgotten when people make these schemes, which is the aspect of learning, where, as the system goes through several exemplars, they will be able to change the representations that they have. As they go through a bunch of feedback, they might be able to change the weights and attentions that they get, and so on and so forth. So when we look at input representation, this is one of the kinds of stimuli that is most often provided in experiments in mathematical psychology. So you have a relatively simple universe where there's a limited amount of features which can be varied systematically so that the experimenter can really explore how people are categorizing within this universe. Here, there's something about how distant the mouth is from the nose, how close the eyes are, and how big the nose is. So stimuli are generally represented in terms of features. In the case of the faces, I was just mentioning that. In the case of the aliens, we had arms, spots, colors, legs, and eyes. And in the literature, again, usually people will talk about features if you have something like the aliens, where the features are binary. When the possible values for each feature or dimension of variation is more continuous, they will talk about the geometry of the stimulus or a geometrical representation. When we get to attentional processes, here is an example. We take a case in which there's only two dimensions and a bunch of stimuli that are represented in that dimension. Let's take the top one, and that's the pure space of variation of how the stimulus vary in these two dimensions. They could even be horizontal position and vertical position, right? And as we apply an attentional filter, what does attention do? Attention takes some dimension and disregards them or looks at them less, and takes other dimension and makes them matter, makes them more salient. In other words, a way of implementing attentional processes in these kind of models is that you can put a higher weight and therefore stretch out the variation in one dimension, and put a lower weight and therefore squeeze the variation in another dimension. And here we can see at the bottom panel that something like that is happening, right? Which dimension is being stretched? Yes. Yeah, the horizontal one. So we see that stimuli that were, I don't know, the two fingers here distant, they become 150% more distant. While on the vertical axis, they become more squeezed, right? So again, this is exactly the idea that not all features are necessarily relevant given the task at hand, and not all features are equally relevant given the task at hand. So sometimes we might have in the alien game, for instance, that one dimension is really not mattering. It should go to 0. We can exclude it. That's the color in most of the things that you've seen last time, I think. But it can also be that some features are sufficient, right, to determine a category. We can, or sufficient, they're necessary at least. So for instance, you can have that arms up are necessary for danger, but they're not sufficient. So in order to have danger, you need both arms up and one out of two other features. Let's say green color and dots, spots on the scale. So in that case, you might want to pay more attention to the arm sub than to the one that has a more probabilistic impact on the category. Uh, Also, in most of these cases, we start with equal weights across all the features, but in real world experiments, what we see is that people come with strong priors as to what is relevant given the task. And one of the critiques that we had in the paper on the aliens was that arms up seems to be a very obvious way of signaling danger and aggression, right? So in principle, one could also try to infer a priori what the attentional weights are. Once we have squeezed and stretched the dimensions, we need to figure out how these things get represented in our cognitive system or our agent in this case. So in the case of the exemplars, what we have is that all the exemplars are remembered, right? By category. And this is something that in the literature is said to be useful in a bunch of contexts. For instance, you know, if you're looking for a mate, you might want to remember, specific individuals. If if you need to rely on caregivers like a child does, it's good to actually recognize them individually. And it allows for all sort of complex structures, right? We haven't seen that there, but I could have drawn that there's a bunch of birds that are centered here, and then there's another cluster here, and then there's another cluster here, right? And by simply collecting exemplars, we don't care about there being a center of the category. We're just remembering them. This has, of course, the disadvantage that it's memory expensive. And while you were filling in the questionnaire, I had tried to make my multi-level GCM much more effective by forgetting some stuff on the way, and it stopped working. So I was swearing a bit. But it is very memory expensive because it means that you need, in principle, as you go up in the word as a 20-something-year-old, to remember all the birds that you've seen out there, right? And that might, if we're just talking about birds, might not be terrible, but then also all the cookies that you've seen and all the ice creams and everything and everything and everything. And that's just not very realistic. However, it's very easy to update. You just need to stuff a new data point there. When we talk about prototypes, what we have is that we're trying to create a representative representation of the exemplar by category. And that's something that, for instance, when you're doing k-means or that kind of things, is defined as a centroid. That is, you look, simplifying a bit, at the average across all these exemplars, given the dimensions that we're using to describe them. And that gives us a measure of where the best possible bird is. This is something that is argued to be good for things like predator and prey. You don't want to have to remember all the deers that you've hunted. You just want to know what is huntable and what is runnable from. This gives you only one cluster or representation by category, and it's very cheap. However, it's slightly trickier to update, but we'll see how to do that. It's actually not that tricky once you thought about that. To be fair to the field, these are kind of two extremes, but there has actually been a lot of work trying to say, can we do something that's in between? It doesn't need to remember all the exemplars, but if exemplars are far enough from most of the other exemplars, I might start remembering them. And once I've seen enough, I will actually create a second centroid, right? Which is, again, the problem of the Chinese buffet. The third model, which is a bit different, is the rules, which I already mentioned, instead of remembering exemplars or creating representation of an average exemplar, there's a question about figuring out a formal definition of the category and then assigning weight to the formal definitions that we can come up with. And that's much easier to remember than, let's say, a bunch of exemplars. You have arms up, danger, or green collar, danger. And it is slightly trickier from a computational perspective to keep in mind and update running the probability of a bunch of rules, especially once we go to many rules or complex rules. When we look at evidential mechanism, that's the probability to belong to each category. We have that we can calculate the average similarity with representation in that category. It doesn't really matter whether it's a bunch of exemplars or simply a prototype. You just take the distance on average. If it's a prototype, it's just the distance from the prototype. Otherwise, you just average it across all the exemplars. Or you can discuss, you can see about whether is the distance from the boundary, right? Not how similar it is to the exemplars all over the place, but actually define where the closest boundary is, and then decide whether the new exemplar is more likely to fall in this very heterogeneous category or into the other, right? Or, there's some work, not very persuasive so far, on evidence accumulation, where, imagine that what you're doing is you're browsing the scene with your senses and you capture one feature at a time, work the probability of belonging to a category along that feature. And then if you're still uncertain, you might sample a second feature and add that information, and then a third, and then a fourth, until you reach a certain level of confidence. And I thought of adding it there because it resonates with some of the stuff that you've seen just before Easter. Right. Finally, yes, we have decision rules, which are, you know, once we have that, let's say these exemplar is a bird, let's say with a 0.9% probability, and a cat with a 0.1%, zero point 0.1, not one, so 90% probability and 10% probability, we need to make a decision. And one way of making the decision is simply to say, let's take the highest number. We're very deterministic. That's the category we're going to pick. Or we can say, let's take the maximum similarity and then add some random noise just to keep it spicy, just to keep exploring a bit. Or we can take what is called the, oh, I always forget where that person come from, but that loose choice axiom, I think that's how Josh pronounces it, which is, since we have probabilities here, we have a 0.9 and a 0.1, let's just have 9 times out of 10 pick a bird, but 1 time out of 10 pick a cat. And when we look at rules, which escape a bit that kind of framework, we could have that if we are testing one rule at a time, the decision rule might be deterministic or it might be probabilistic. If we have more than one rule, we might actually combine their predictions according to the weight. And then yes, learning and time, it's often underexplored. There's some evidence accumulation in the sample and how we process the stimulus. We know that because when we tell participants to be very fast, we affect their performance. So there's something that goes on there. It's not really much in these models. There's some time, as we will see in the second part of the lecture, in the fact that we develop the categories as we go along in the experiments. A lot of the early experiments were assuming that participant had already seen all the training exemplars, and therefore their category would stay static. Uh, and that meant that even seeing new exemplars wouldn't change the way that your category was. But that's something that we can very easily do with contemporary probabilistic programming languages. There is something about learning of the attentional weights, and we will see that in traditional models like the GCM or prototype models, that is actually tricky to do. And there's some attempts at using neural networks to update weights running or reinforcement learning to update weights running, but they tend to have very big problems in terms of parameter recovery. Uh, I had a master student a couple of years ago that was reworking the GCM to include new stimuli running, and that's the kind of code I'll show you. And then we were trying to learn attentional weights using neural networks on top of the GCM, and that just was impossible to recover the simulation values. So that's something that is still pretty open in the field. I was talking to Josh about that, and he has been using the alcove, or actually, he has condemned a couple of master students to use the alcove in their master thesis, and they show exactly the same problem. They just don't recover the parameters in the simulation. When we talk about rules, actually, in learning rules, there is a very neat way of applying Bayes' theorem to just update the probability of the rules, and therefore we actually have course notes that work and recover the parameters for that. Yes, before we take the break, there has been a lot of effort in the last 10 years in trying within categorization processes to build a cumulative approach to these models, which is actually very rare compared to other domains of cognitive modeling. There's a couple of papers that try to advocate for how do we formalize categorization models using shared standards, and that's where the template that I showed you before comes, and the development of our package that implements all the main categorization models that have been suggested in the literature in a forward implementation, meaning that there are scripts that can play whatever task you give them and generate a simulation of the choices of the agent, but cannot infer from the agents, from the participants' data, what the parameter values would be. And actually, oh yeah, I actually wanted to do this before the break. That's also, as we think about categorization, right, the problem is in this simplified scenario, we have two categories. We have a bunch of features. We're trying to learn which of these features are relevant for the decision, right? How is this different from classification? Right, where classification is something that comes more from the machine learning world, which is about exactly trying to identify the best possible combination of weights and features that accurately predicts the true category, right? Yes. Yes. Well, so yeah, I if I paraphrase correctly, right, we have two traditions. One is categorization research, the other classification research. And the classification research has been mostly concerned on how do we get a high accuracy in the true category, while the categorization research has been focused on how do we reproduce an organism's mechanism of choice. And the current trend in neural networks then came in the field and said, well, organisms are using very complex brains and they are not being fed like these features that are binary or anyway have a very limited range of possible values. They are fed like very noisy input. So if you're talking about trying to replicate how organisms works, maybe the classification field has much to offer to you. To which the categorization field then replies things like, well, but you throw like a cannon at the problem. And what we've been doing so far is to try to isolate aspects and try to test their implications. Yes, Sabrina? Yes. Mm-hmm. Yeah. So in a sense, from a certain aspect, the structure of the problem is exactly the same. So what changes is how you approach the problem, where a classification approach will try to get the true class as accurately as possible. The categorization approach will try to say humans make errors, if we're talking humans. What are the simplified models that will allow us with parsimony to capture the patterns of errors, right? If you want, yes. And and that means you could also use traditional classification approaches like a convolutional neural network, but you need to do that in a way that allows you to better understand how the organisms are doing that. While the classification tradition doesn't care about that, actually wants in principle to get better than humans. Yes, works. Yeah. Yeah, so imagine that, well, we know that people are falling for some spam, otherwise it wouldn't exist, right? And so the idea would be a spam filter will be in the classification field and try to sort of screen out all the spam messages, right? And categorization approach would say, well, actually, we want to understand what makes some spam more effective than others. Some features that trick people into responding to the spam, and we have a set of models that we developed over the years that might help us identify where these error patterns come from. Right? Yeah. And there's lots of overlap, but it's just that the structure of the problem is so similar that I thought that we should reflect a bit on that. So with that, we'll make a break and I'll go and fetch some plates and knife. Maybe I should actually stop the microphone first. Sharing. Okay, we'll start again. So what I want to focus on is to give you another example of how we code a categorization model in practice. And we'll do that on the generalized context model. So the generalized context model in the scheme that we've seen before represents its input as potentially geometric traditionally, but in our case, we will have binary features. And its distances are, in the literature, either Euclidean or Manhattan distances. And what the difference is, imagine that you have point A and point B. A Euclidean distance is the distance between the 2 points. And a Manhattan distance is a distance that cannot go straight from one point to the other, but separates the two dimensions. So it says there's a distance of 1 on the vertical dimension, and there is a distance of 1 on the horizontal dimension. So the total distance is going to be 2, right? What difference does that make? Well, it has a few uh, differences. So it tends to increase. So the Manhattan distance tends to increase faster than the Euclidean distance. But as we will see in practice, it doesn't matter that much because we will put a scaling factor. We will put a factor in the model that allows us to go from a measure of distance to a measure of psychological similarity or cognitive similarity. The attentional processes of the GCM are weights that need to sum up to 1, meaning that if we have 2 dimensions like there, vertical and horizontal, we need to have something that sums up to 1. So it could easily be zero point 0.5 and zero point 0.5. But if we think that vertical shouldn't have that much weight, then horizontal will need to go up to 9, right? In terms of intermediate representations, it has exemplars, meaning that it remembers all of these stimuli that it has seen. In terms of evidential mechanisms, what we have is that the distance is not taken into account rho, but actually what happens is that it gets decayed in an exponential fashion over distance. We'll see the formula. And the way that then the similarity with the category is calculated is by taking the similarity with each single exemplar and then doing the average of that. The decision rule traditionally is a loose choice axiom, meaning that it's probabilistic. If it's 0.6 distance, so if we sum up the distance from category 1 and from category 2 together, and we divide the single distance between category 1 by this total and the distance from category 2 by this total, we get probability from 0 to 1. And if we have that the distance from category 1 is 0.8 in this normalized scale, 80% of the time we will choose category 1, but 20% category 2. And the way that learning is conceptualized in this model is in terms of having a training versus a test set. So due to the fact that this model was developed in the late 70s, early 80s, it was mathematically very convenient and computationally very convenient to have a predefined categorical space that the subject had already been exposed to. Once we have that well established in the model, then it becomes relatively cheap to simply compare the new exemplars to these existing categorization training set and then calculate how the agent behaves. These, in an interesting, the map is the territory kind of movement, meant that as psychologists tried to test these models, what they actually ended up doing was to have participants locked in their psychophysical lab for 4 or 6 hours, going through the training set of exemplars again and again and again until they were sure that there was no error, right? And then the experiment proper would start, and they would be exposed to new exemplars, and they would go through register, record like the reaction times and the choices and so on and so forth. And to the point that even I think it's the most recent exposure of these model in Lee and Wagenmacher's book on Bayesian models of cognition actually still assumes that you're already being trained for several hours on these set of categories. We don't need to do that. This is the representation in terms of DAGs, platelet notation of directed acyclical graphs of the model, where we have that there's a bunch of subjects that go through a bunch of trials. In each trial, they make a choice that we can observe, right, based on some features that we can observe and some category that we get as a feedback, right? Given the features, right, we can calculate a distance from the exemplars in memory, which are shaped by the weights in which space they are. We can see that the memory is dependent on the trial in the way we're conceptualizing these model, because we move away from the original formulation and we say actually it should only be the exemplars you've seen. So it's inside the plate of trials, while the weights aren't changing, right? They're inside the plate of subjects. Different subjects might have different weights, right? But they don't change over time. This is a very strong assumption, right? But we're already relaxing how the model is. Given the distance, we need to calculate the cognitive or psychological similarity, which we do using a scaling factor, which might be different by participant, right? But it doesn't change by trial. And given the similarity to the two categories, we calculate a rate, a probability of picking category 1 versus category 2. And here we might have a bias, right? Participants that are very scared of these aliens and will tend to say they're not dangerous a lot of the time, that they're dangerous a lot of the time, or participants who just don't want to say they're dangerous, right? The model that we can use calculate distance as Manhattan distance, and we can there write it as the weight times the distance between each single feature of these new exemplar, and separately the previous exemplar, the previous exemplar, the previous exemplar, and so on and so forth. And then we just sum. The similarity is calculated as the distance, or actually e to the power, so the exponential of the distance and minus a scaling factor c, which we're going to explore in a second. Right? The rate, as I was anticipating before, is given by the similarity to category 1 divided the sum of the similarity to the existing categories. So it's renormalized on probability scale. Since sometimes people use Manhattan distance, sometimes Euclidean distance, this is actually the general formula for distance of this kind, where you have that there's a sum of the weight times the distance between the features. to the power of r, everything under a root of r. And then we have that if uh, r is 1, we get Manhattan distance. If r is 2, we get Euclidean distance. So that makes it actually easy you could even estimate that from your data. So we go and code. We take a very simplified setup. So that actually leaves you completely free to use the GCM if you want to run the GCM on the Alien game. And we take data from a paper by Krashke in 93, which basically has 2 dimensions: the height of a specific line where it appears on the screen, and the horizontal position of that line where it appears on the screen. And unbeknownst to the participants, there is a category boundary exactly in the main diagonal, which means that all the stimuli above are category 1 and all the stimuli below are category 2. In total, there's 8 stimuli, and each participant is exposed to 8 sequences with all 8 stimuli in random orders. So what we can do is we can simulate this data. We have the stimuli that have 1, 2, 3, 4, 5, 6, 7, 8. They have different values for height that we can reconstruct from the plot here from the paper in which it was. Right, so we can say that in height, this is 1, this is 2, this is 3, this is 4. And the same for position, 1, 2, 3, 4. We do the same for position. We tell the model which category they are. And then we can plot them to make sure that they look like what the stimuli in the paper were. And so here were they in the papers, right? And here are the true ones. And you can check them later if you want, but I'm pretty confident that I got them right. So we then run the experiment, and the way that we do it is we create the sequences of the stimuli as they're presented to participants. So we can create an empty sequence and then do a 8-time repetition for I in 1 to 8, and we simply randomly sample from this sequence of 1 to 8 without replacement, meaning that the same stimulus cannot be picked up twice. And then we append these 8 sequences, the one to the other. And then, given that now we've identified the stimuli just by their label, 1 to 8, we then create a table where we associate the actual height, position, and category to the stimulus ID. Why am I spending some time on this? Well, it's because actually the fact that there are 8 repetitions and 8 stimuli does not have only trivial consequences on the way we can build the model. Depending on the structure of the experiment, actually, the very same model with the very same priors might perform very differently, right? There's a paper that details all of these stuff. It's called "The Experiment is Just as Important as the Likelihood in Understanding the Prior." And it's something that is something that I have to continuously point out when I act as a peer reviewer, because people take a well-validated model on a specific experiment and just use it on a different experiment. And it's, in my very painful experience, absolutely non-trivial that a model will keep on working in a different context. One of the things that I was working with Sarah, the student who developed some of the code that you will see on the GCM, is that actually, for instance, making the alien features continuous would have drastically changed the ability of the model to work on them. It would have been actually much more effective. But when we planned the experiment, we had no idea of that, right? So we had to do a lot of extra legwork in order to make the model work because the features were binary. So that's the kind of things that actually is very important to know in advance. Good. So then we want to code the function of distance there, and we're using the Manhattan and the function of similarity, as we've seen before. And then since I have a hard time grasping the abstract equations, we see how different values of C will affect distance and similarity, or similarity from the same distance. And here is the code to generate the small simulation, but basically on the x-axis, we have the distance. In color, we have the different C scaling factors. On the y-axis, we have the measure of similarity that's outputted by the equation once you have that distance and that scaling factor. And we can see a shape that we've seen before when we were doing exponential decay of memory, where if we have low scaling, we see a linear decrease of similarity with distance. As we increase C, we see a more and more drastic decrease of similarity as distance increases even just by one, right? Meaning that the way that the agents will perceive the new stimulus, right, might be, well, as long as we are in the same space, there might be a bit of similarity, or as soon as I'm far enough from the category, nothing will be similar there, right? Yeah. Then we can code the GCM, and I forgot to make it, or not forgot, but I didn't have the time to make it on white, that one. Because the one I have in the course notes goes beyond the one page. So when I was trying to make a screenshot, it didn't work. Uh, but basically what it does is a function that takes a few inputs, in particular the weights, W, the C, that's the scaling factor, the observations, right? That's the uh, exemplars that it has seen, and category one, that is a list of which of these observations belonged to danger, or in that case, category one, whatever it was. And so we we say there's as many trials as the observations and rows of observation. For each of the trials, there's just some debugging stuff. But if this is the first trial, or if there is any category with no exemplars, just output a category at random, right? Because you have no idea what it is. So output a rate of 0.5. Otherwise, for each previously seen stimulus, assess the distance and similarity, right? So for all of the stimuli in the sequence between 1 and the previous trial, I minus 1. So let's say if this is the 10th trial, it will go from 1 to 9. Right? Calculate the similarity using scaling factor C on the distance that you can calculate between observation I and observation E. And then save these similarities because we might want to keep them in mind, right? Then we calculate the probability of saying 1 by dividing similarity to 1 by the sum of similarity to 1 and 2. And we have that the numerator is the mean similarities to 1, and the denominator is the mean similarities to 1 plus the mean similarities to 2. And then we get that the rate or probability of picking 1 is the numerator divided the denominator, and then we append it. So we keep those. Then once we have that function, we can use that function to go through the experimental setup that we programmed before. We can have simulate responses. That takes an agent, it takes a weight, and it takes a scaling factor. Then it takes the observation from the experimental table that we've done before and the category from the experimental table that we've done before. And then here I simulate three weights just to visualize things. If weights are equal, then we have zero point 0.5 and zero point 0.5 on height and position. If the weight are skewed in the first way, we have that no attention is paid to height, but all attention is paid to position. And if we have skewed 2, we have 10% of attention is to height and 90% to position. We then feed the observations, weight, and C to the GCM function, and we get out the responses. And then let me remember what this was. Okay, yeah, and then we save what we've been doing. And as we're saving it, we also check whether the choice was correct and what's the cumulative performance as we move along the trials. Then we do our usual parallelization, right? We create a session, we evaluate how many workers there are, how many cores there are in your computer. We give it some parameters across which to run. So here there's 10 agents, and there's possible scaling values that go from 0.1 to 2 in steps of 0.2. And there's 3 possible weight setup. And then we just run the simulated responses, which allows us to explore what's the impact of weights and what's the impact of scaling factor in this specific problem. And so, as I usually do, you have 2 panels. In these panels, on the x-axis, there's the trial. On the y-axis, there's the performance. The 3 panels are the equal weights, the completely skewed weights, and the less completely skewed weights. And in color, you have the different scaling factors. Here, I just invert the panels. The panels are C, the scaling factor, and the colors are the weight. Have a look at it for a second. And then what do you learn about the impact of scaling and weights there? I think that if we look at these panel, it's slightly more obvious, right? Anybody wants to say what they see at the top? So what happens when we have a low scaling factor, meaning that the distance and similarity are connected linearly? Slao, it's not affected. It's also a chance level. Yeah. Yes. So 4 or 6 or 8. As the scaling increases, yes. Yes. So let's try to look at the stimuli, right? Maybe this is easier. Why do we need a high scaling? That is, why do we need a strong exponential decay in this specific problem? So this one, oh yeah, and these two, right? So they're pair, almost obvious pairs there, right? Yes. Mm-hmm. Yep. Yeah, exactly. So what happens is that you have some stimuli that are very close and some stimuli that are very far, even within the category, to the point that 5 and 7 that are across the category, they are closer than 5 and 2. So by increasing the scaling, basically you increase the focus that 5 will have on its closest. And if it's high enough, it will only see 3, basically, right? And it will never go wrong. And that's the same for 7 and 8. Because in the Manhattan space that we're inhabiting, 7 and 8 are only separated by 1, while 5 and 7 are separated by 1 and 2, right? 2 steps to get from one to the other. So by really emphasizing the scaling, by really focusing only on the nearest neighbor, we always get it right. Why? Well, we haven't commented on that, but if you look at here, the equal weights are the best performing once the scaling is high enough. The skewed, like strongly skewed, where it only pays attention to one dimension, is the worst. And the middle way is the ones that are only partially skewed. So why do you think that equal weights are the best performing algorithm there? Right, you look at the space, at the topology of the space. Basically, equal weights means that position matters as much as height, right? And the way that the geometry of this space works is that there is just as much variation, relevant variation on the one axis as on the other axis. So as we move away from equal weights, we lose some of the information. Does that make sense? So if the stimuli were distributed in a different way, we might get a different pattern, right? And that's where we want to do these plots and try to understand what works in the different experiments. Okay. This is the um, stand code for the model, where we get as input the number of trials, the number of features, which of the stimuli are category 1, which decisions are made on a trial by trial basis, which stimuli are shown on a trial by trial basis, the observation, and whether there is a bias for category one over category two. And then we have the priors for weights and the priors for the scaling parameter, which we can feed to the stand code so we can more easily experiment. We then need to transform the data because we want for the model to have a separate list of which exemplars are of category one and which exemplars are of category two. And that's really is a chunk of code that does that. So it goes through all the trials, and then it says that the cat2, category two, is really category one minus one in an absolute term. So if category one, if the stimulus was category one, one, it becomes zero. If it was category one not, right, zero, it becomes a one. So cat2 is the mirror of cat1. And then we simply create a list of indices of which one is category one and which one is category two. In terms of parameters, we have the weights and we have the scaling. We are making them two specific forms of parameter. So the first one is we're saying that there's a simplex, and a simplex is a Dirichlet function which has n partitions of the space between 0 and 1. Right? So in this case, we have two features. So we're dividing the space between 0 and 1 in two parts. If we had five features, as in the alien, we would divide it in five parts. By defining the weights as a simplex, we ensure that they will always sum up to 1. The second is scaling factor, which is defined as logit C, meaning we're defining it on a space, what's called on a logout space. And I want you to take a minute to think as to why we are modeling it as a logout space. Scaling parameter, yes. Weights are between 0 and 1, but they can be more their sum has to be on a 0 to 1 scale, so we use the simplex. The scaling, which we had seen, for instance, going from 0.1 to 2, we are putting it also on a logout or on a logout scale. So what are we doing to that scaling parameter? Yes? Yeah. Mm-hmm. Yes. Okay, so what we're doing is we're saying, watch out, the scaling factor needs to have some boundaries. And why do we need boundaries? Well, if we go back and look at the plot, right? First of all, if we go below 0, what we see is that the more think, how is it? The more the distance, the more the similarity, which makes no sense, right? So we want to put a boundary at 0. The logouts does that, but it also puts a boundary at 1. It doesn't need to be 1, because then what we could say is simply times 5 or times n. So now simply we have a boundary between 0 and n. But why do we need from that plot a boundary on the high values of the scaling factor? Look at the distance between separate values of the scaling factor. How much of a difference increasing the scaling factor does. Right. Yes? Yeah, so as we're increasing the exponential decay, the same length of step makes less and less of a difference. And if you remember when we discussed the MCMC sampler, when we have these situations, what might be happening is that the sampler gets lost, because doing a step in that direction gives you almost exactly the same results as where you were before. And therefore, it can make another step and it gives almost exactly the same results. And it makes another step, and there's basically no stopping it from going that way. So it tends to get lost in those places. So what we can do is we can actually artificially put a boundary here and say, we don't want you to go too far in that direction. This is not something that I thought a priori as I was working on the model. It's something that came out of the model getting actually lost in those places. And these seemed a good solution, because just working with priors, we're still having it getting lost a lot. We were here, yes. So then we have a transform parameter section, where what we do is we generate C by doing the inverse log odds of what we just defined and multiplying it by 2. So basically, we bound it between 0 and 2. If we had multiplied it by 5, we bound it between 0 and 5. And then we make sure that if the rate is very close to 0 or very close to 1, we sort of squeeze it back. I think it's in the next one. Well, but we just say that we don't want a rate of 0 and a rate of 1. Then we go through all the trials, and we need to calculate the distance from the observation to all the previous exemplars, right? And so here we do that same loop as before, right? We go from 1 to n of trials, and then within each of those loops, we go from 1 to the previous trial, right? To calculate things. And I'm not gonna go through the details of that, but you can look at that in the course notes. And then we calculate the similarities, we calculate the rate, and if the rate is very close to 1, we push it back. If the rate is very close to 0, we push it back. And then we save it, right? Then the model is actually very simple. Once we've defined all of that, the model is simply a Bernoulli distribution or a rate. And the priors for our two parameters, the weights and the log odds of the scaling factor, are simply those that we feed into the data because that allows us to try out different things. So then we want to see whether we can recover the weights. So we compile the model, we fit it to a bunch of data that we generated before in the responses when we simulated the responses of the agents. And then we looked at when we have a true, very low scaling factor, it's really hard to recover the weights. As we increase the scaling factor, the which color is this? Like the pink, light reddish thing is the equal weights. It should be a 0.5. And it actually starts emerging and it gets more and more pointy until, I don't know, 1.1. And then it keeps the same pointiness. It's nicely recovered. The green should be 0 because it's the fully skewed one. And again, we can see that it starts emerging very early, but it's very uncertain until over time it becomes more and more pointy. And the same for skewed 2, that should be 0.1. It's very uncertain, but then it gets very nicely recovered. Right. So the model seems to be working. Then we want to see whether we can recover scaling, right? The panel is, again, the true value of scaling. And then so I put in the same panel the posterior estimate for scaling in the model that has equal weight, in the model that has skewed weights, and in the model that has partially skewed weights. And what we can see is that the model moves with the actual scaling value, but that in particular, only paying attention to one dimension might make it harder to recover the true value. Is this good enough, you think? And yes, I thought it was actually good enough. And that's why we could go multi-level if the lecture wasn't done. So tomorrow we'll be working on your models, but I hope that these gave you some inspiration. And what I'll ask you to do by the next lecture is to have a look at the course notes on the prototypes and the rules and see if you have questions on that. And then I'll keep on going through the code and everything. But my perspective on the very last lecture in 2 weeks is that probably it's best dedicated to group work and me giving you extra support so that you can finish the portfolio and feel relieved, right? So let's try to do it like that. So next week, I will finish going through the GCM and we'll discuss what you haven't understood on rules and prototypes. Thanks for today.